Imagine you have a secret code that you can't crack. Every time you receive a message, it seems like a jumble of random letters, leaving you puzzled and wondering what it means. But what if there was a way to unveil the hidden message? Enter the Hidden Markov Model (HMM), a powerful tool that can unlock the mysteries hidden within data. At its core, the Hidden Markov Model is like a detective searching for patterns in a sea of information, whether it's predicting the weather, understanding spoken language, or analyzing DNA sequences. HMMs are the sleuths of the mathematical world. What makes HMM so intriguing is their ability to reveal hidden states. You can think of these states as the missing puzzle pieces that shape the observed data. Just as a magician pulls a rabbit out of a hat, HMMs can pull out the hidden states behind the information you see. But how they do it? Well, HMMs rely on the power of probability. They estimate the likelihood of transitioning from one hidden state to another based on the observed data. It's like solving a puzzle by analyzing the probabilities of different pieces fitting together. One fascinating aspect of HMMs is their Markov property. This property states that the probability of moving to a new state only depends on the current state, not the past. It's like living in the moment and making predictions about the future without dwelling on the past. So whether you are deciphering coded messages, predicting stock market trends, or understanding the complexities of speech, the Hidden Markov Model is your trusted partner in unraveling hidden truths. It's the secret weapon that brings clarity to the enigmatic world of data, one hidden state at a time. Get ready to embark on a journey of discovery as we delve into the captivating realm of Hidden Markov Model. According to recent studies, AI machine learning related job postings have increased by 344% in the past 5 years. Companies across the globe are actively seeking professionals who can harness the power of data and build intelligent systems. The average salary is $150,000 in the US and 15 lakhs per annum in India. With that having said, hey everyone, welcome to Simplilearn's YouTube channel. But before we dive into that, don't forget to like, subscribe and share. So without any further ado, over to our training experts.
A hidden marker model (HMM) is a statistical model utilized to depict the probabilistic connection between a sequence of observed data and a sequence of concealed state. It's commonly employed when the underlying system or process generating the observations remain unknown or concealed, which amounts for its name, the hidden marker model. The primary purpose of an HMM is to forecast future observation or classify sequences based on hidden processes that generate the data. An HMM consists of two distinct types of variables. First one is hidden states and the second one is observations. Hidden states represent the underlying variable responsible for generating the observed data, but they cannot be directly observed. But the observation other side denote the variables that are measured and observed. So the association between the hidden state and the observation is established using a probability distribution. So the hidden Markov model HMM defines the relationship employing two states of probabilities. The first one is the transition probabilities and the second one is the emission probabilities. The transition probabilities outline the likelihood of transitioning from one state to another hidden state. And the emission probabilities describe the probability of observing an output given in a hidden state. So let's move forward to the application of hidden Markov model. So the first one is speech recognition. HMM are widely recognized for their application in speech recognition. In this field, HMMs are employed to model the various sounds and phones that constitute speech. The hidden state represent distant sound of phone, while the observation are the acoustic signal produced by the speech. And the second one is NLP, natural language processing. So this is the another significant application of HMM is in NLP. In NLP, HMMs are utilized for tasks like part of speech tagging, named identity recognition, and text classification. In these applications, the hidden states are commonly associated with the text. The goal is to estimate the hidden state sequence which correspond to the structure or meaning of the text based on the observed word. The third one is bioinformatics. HMMs find extensive application in bioinformatics, where they are employed to model sequence of DNA, RNA and proteins. In this context, the hidden state represent different types of residues, while the observation correspond to sequence of residues. The objective is to estimate the hidden state sequence which represent the underlying structure of the molecule based on the observed residue sequence. And the fourth one is finance. Finally, HMMs have also found application in finance, especially in modeling stock prices, interest rates, and currency exchange rates. In these applications, the hidden state correspond to different economic states, such as bull and bear markets, while the observation represent the stock prices, interest rate, or the exchange rates. So after seeing application of hidden Markov model, now let's see some advantages and the disadvantages of the hidden Markov model. So advantages of hidden Markov models are flexibility. HMMs are flexible and can be applied to various domains and problems such as speech recognition, NLP, bioinformatics, and finance. They provide a versatile framework for modeling sequential data. And the second one is probabilistic modeling. HMMs are based on probabilistic principle, allowing them to handle uncertainty in the data. They can effectively model and represent the probabilistic relationship between hidden state and the observation. And the third one is capturing temporal dependency. HMMs excel at the capturing temporal dependency in sequential data. They consider the order and transition between hidden state, which is crucial in many real-world scenarios. And the fourth one is handling noisy and incomplete data. HMMs are robust to noise and incomplete data. They can handle missing observation or deal with data containing errors or certainties, making them suitable for real-world example. So now let's move forward and see the disadvantages of hidden Markov model. So the first one is independence assumption. HMMs are assume that the current hidden state only depends on the previous hidden state. The market assumption might not always hold in complex real-world scenarios where the current state could depend on multiple previous states or the entire history. And the second one is limited modeling of long-term dependencies. Although HMMs capture short-term dependency, well, they may struggle to model long-term dependency in sequential data. Okay, the third one is lack of transparency. HMMs are considered black box models, meaning that the relationship between the model parameter and the real world phenomena may not be easily interpretable. Understanding the inner working of the model can be challenging. And the fourth one is model selection. The selection of appropriate number of hidden states and setting models parameter can be complex task. Determining the optimal structure and the parameter for the HMM often requires domain knowledge and experimentation. So overall, while HMMs have proven to be the powerful models for sequential data, they are not without their limitation. Advances in deep learning and other sequential models have introduced alternative approaches that can overcome some of the disadvantages associated with the HMMs in the specific context. So moving forward, we will see hidden Markov model algorithm steps. Okay, so let's move forward. And the implementation of the hidden Markov model algorithm can be outlined through the following steps. So let's see step 1. Specify the set of possible hidden states and the observation. Step 2. Establish the initial state distribution, which represent the probability distribution over the initial state. And the third one is define the probabilities of transitioning from one state to another, forming the transition matrix that depicts state transition. Step 4. Specify the probabilities of generating each observation from each state, creating the emission matrix that describes observation likelihood. And the fifth state. Train the model by estimating the parameters of the state transition probabilities and the observation. This is achieved using Baum-Welk algorithm or the forward-backward algorithm. The parameters are iteratively updated until converge in the reached. Step 6. Decode the most probable sequence of hidden states based on the observed data. The Modelby algorithm is employed to compute these sequences, enabling prediction of the future observation, sequence classification, or pattern detection in the sequential data. And the final is step 7. Evaluate the performance of the HMM by utilizing metrics like accuracy, precision, recall, or F1 score. So in summary, the HMM algorithm involves defining the state space, observation space, and the parameter of the state transition probabilities and the observation of likelihood. The model is trained using the Baum-Welk algorithm or the forward-backward algorithm, followed by decoding the most probable hidden state sequence using the Modelby algorithm. Finally, the model's performance is evaluated using the appropriate metrics. So moving forward, we will see the small demo of how you can use HMM model. Okay. So hi, welcome to the demo of HMM. So here we will predicting the weather. So problem statement is, so we have the data of historical data and on a weather condition. So the task is to predict the weather for the next day based on the current day's weather. Okay. So let's import the some libraries. Before that, I will change the name, Hidden Markov Model. Okay. So let's import some major libraries like NumPy, Pandas, Matplotlib, Seaborn, and the HMM itself. So first I will write import NumPy as np, and the second I will like to import Pandas as pd. Then third one is import Seaborn as sns, and the fourth one I like to import from Learn import HMM. Okay, you have to import or install HMM library. You can use pip install HMM, and again you have to use pip install HMM learn. Okay, then one more, import matplotlib dot pyplot as plt. Okay, let me run this. Yeah, it's working, right? So the in the second step we will define the model parameters. Okay, so let's define the model parameters. It's like, okay, para equals to, first will be sunny, okay, and rain. Okay, so n para equals to length of parameters. Okay, then I will like to print number of hidden state. Okay, that is n para. Okay, so now here I will define the observation space. Okay, so here I will write observation equals to dry, comma, wet. Okay, and n observation equals to same the length of observation, and here I would like to print number of hidden, or I will write that observations, comma, and observation. Okay, let me run it. So as you can see here, the number of hidden state is 2. See, you can sunny and rain, and the observation is 2, or dry or wet. Okay, so the start probabilities, transition probability, and the emission probabilities are defined as arrays. Okay, the start probability represent the probabilities of starting in each of the hidden state. The transition of the probabilities represent the probabilities of the transitioning from one hidden state to the another, and the emission probabilities represent the probabilities of observing each of the outputs given in a hidden state. So in initial stage, the distribution will be defined as a state probability, which is an array of probabilities that represent the first state being sunny or rainy. The state transition are defined as the transition probability, which is 2 by 2 array. Okay, so it's like this. So let's move to the, defining the initial state distribution and all. So here I will write para probability equals to np dot array 0.6, 0.4, and I will write here print the para probability. Okay, and then para probability. Okay, so here I will define the state transition probabilities. So I will write here transition probability equals to np dot array, and here I will write 0.7 comma 0.3. It's like 70-30%. Okay, then 0.3 and 0.7. Okay, so now I will print the transition probability. So I will write trans underscore probability equals to np dot, sorry, it's my bad, comma trans probability. Okay, here we don't have to write underscore. Yeah, so now I will define the observation likelihood. So for this emission probability equals to np dot array it's like 0.9 comma 0.1, then I will write 0.2 and let's give 0.8. Okay, so here let's print the emission probability emission underscore probab. Okay, and let me run it. Okay, np array trans probability 0.7 0.3. Okay, okay, so here let's add okay, yeah. So as you can see, the para probability is 0.6 to 0.4, then the transition probability and the emission probability. Okay, so let's create an instance of HMM model and set the model parameters. Okay, so the HMM model is defined using the HMM categorical HMM class from the HMM library. We already imported the library HMM learn. An instance of, so here the set of n hidden states and the parameters of the model are set using the start prop. Okay, so let me do for this for the better visual, and here I will write model equals to HMM dot categorical HMM and n underscore components equals to n parameters. Okay, then m dot start probabilities equals to, okay, this para, okay, but para underscore probability. Okay, then m dot transmat underscore equals to trans underscore probability, then m dot emission probability equals to emission underscore probability. We already defined here, as you can see, the trans, the para probability, the emission probability. Okay, so let me run it. Okay, and comp, it's n components, yeah. So now let's define an observation sequence. So a sequence of observation is defined as the one-dimensional NumPy array. So the observed data is defined as observation sequence, which is sequence of the integers representing the corresponding observation in the observation list. Okay, so here I will define observation sequence equals to np dot array 0, 1, 0, 1, 0, 0. Okay, then dot reshape and then -1, 1. Okay, so here let me write observe. Okay, no error, so I can so it will give me the output. As you can see, it's coming in like one-dimensional array. Okay, so moving forward, let's predict the most likely sequence of hidden states. So for that we have to write here hidden state equals to model dot predict observation sequence. Okay, so print hidden state. Okay, so it's not the model, it is m. So as you can see, it's coming. Okay, 0, 1, 0, 1, 1, 1, 0. Okay, so the most likely hidden state is this. It's coming like this. So now what we have to do, we have to decode this observation, this 0, 1, 1, 1, 1, 0 observation using the Modelby algorithm. Okay, so for that we have to write here log probability hidden, okay, it's hidden state. Okay, equals to m dot decode observation sequence, comma, so length equals to length of observation algorithms equals to y2b. Okay, so here let me print the log underscore probability and print the hidden states. Okay, okay, so len takes no keywords argument. Okay, so for that we have to write here observation underscore algorithms. Okay, again okay, so here I will write observations sequence okay, it was right before. Okay, so observation sequence, OBS sequence. Okay, OBS sequence, so let me run it. It's saying length. Okay, it's vitaB, and then it's print. Okay, let it no keywords arguments. Algorithm and the observations. Okay, I forgot one thing. It is sequence. We can write actually like this. Okay, then comma. Yes, let me run it now. Okay, it's coming. So as you can see, the log probability is -6 point this, and the hidden state is this. So this is a sample like how the algo to implement the basic HMM and use it to decode an observation sequence. So let's plot the results. Okay, let's see. So SNS dot set style grid. Okay, PLT dot plot hidden states, comma -O. It's okay, label we don't want to write. Okay, we can write the label also. So here label equals to hidden state, then plt dot x label, it's time, and plt dot y label, like most likely hidden state, and here plt dot title is sunny or rainy, and then plt dot legend we can write, and then plt dot show. Okay, so let me run this. Okay, so here we can write the white grid. So as you can see, finally the results are plotted using the matplotlib library, where the x-axis represent the time steps and the y-axis represent the hidden state. The plot shows that the model predicts that the weather is mostly sunny with a few rain days mix. So as you can see, it's mostly sunny. Okay, see 0 1 1 1 sunny, and these are the hidden states, and these are the 0 again. Okay, as you can see 0 1 triple 1 double 0. Okay, so this is how you can implement hidden Markov model in your projects. So these are the some library I use, the NumPy, Pandas, and the Seaborn. Okay, and here we so here we describe the parameters and the observation, and here the probability we get, and here we implement the HMM, and here hidden states now finally. Okay, so here we wrap up with this HMM model. Okay, if you have any question, please add it in the comment section below. Our expert will get back to you soon. So, and do subscribe to Simplilearn channel for the more updates. Till then, stay safe and
Hi there, if you like this video, subscribe to the Simplilearn YouTube channel and click here to watch similar videos. To nerd up and get certified, click here.